Hello everyone, today I will talk about our paper Enhancing BERT Performance with LLMs, Structured Data Augmentation for Biomedical Entity Recognition. This is our training pipeline. We have the nodes, then the annotator will annotate nodes. The annotated nodes will feed into BERT to train the model. And then what we added from this box, we propose to, after the annotated nodes, we feed them into LLM and to generate more synthetic nodes to feed the BERT. We have several steps of generating annotations. The first step is prompt template, and second step is supervised fine-tune LLM, and the third step is we need to convert LLM output to ANS, and I will talk about each one individually. Then the first step is create prompt. We have the annotation guideline, we have the annotations, and in this step we will define the data model schema, and because we need to convert the schema to JSON, so we convert the schema into prompt template. And for the second step, supervised fine-tune LLM, we have the annotations, we have no task, we take this as an input to feed to Llama 3, and we have the annotations, no task, then we will have the ground truth label. This is when we train the model, the ground truth it is. And the third step is convert LLM output to ANS. And because LLM is struggling with directly generated offsets, so we are taking the intermediate step of finding a context to help the entity offsets. So the context that is define the sentences around the entity of concept. We take this example. So in step 1, find the context offsets by string match. Then that is, we can use strict match or fuzzy match. After we find the context, then we can find the in context entity offsets by string match. Then we can generate node level entity offsets. Then we can convert into an AN file. And in our paper, we'll focus on to solve 3 research questions. For research question 1, which model LLM or BERT is more effective as a source of generating auxiliary annotation data to improve BERT performance? Research question 2, given augmented data from different models, which is the best strategy to combine them with the original label data during training? And for research question 3, what factor of augmentation set influence the performance of the BERT-based NER model? In this slide, we are talking about the data set we are using. We are using NCBI disease. The source is PubMed abstract, that is the disease NER benchmark. It nearly have 800 total of the nodes. And for the proprietary data set, we are using clinical notes, that is real world clinical NER, and we have 2,306 total of medical notes. And for auxiliary data set, we're using BC5, that is a PubMed abstract also, and that is in domain for NCBI. They contain about 1,500 abstracts. And for BioRed, that is also a PubMed abstracts, that is in domain for NCBI, that is out domain for proprietary data set, and it nearly have 6,000 abstracts. We also have the NCBI validation set and also have proprietary validation data set. So in this slide, we started our first research question. So given the LLM underperform compared to BERT on NER tasks, which model LLM or BERT is more effective as a source for generating auxiliary annotation data to improve BERT performance? So this table summarizes the performance of LLM, the original BERT model, and the BERT model trained with auxiliary annotations. So in both NCBI and proprietary citing augmenting BERT with LLM-generated annotation here using BERT-L consistently improve performance over using no augmentation and yields better F1 score than BERT-generated annotations. So for example, on NCBI test, BERT-L achieved FN score is 89.86 and marginally higher than BERT-B. So similarly, the proprietary test set BERT-L reached about 86.5 outperform BERT. So this result suggests that LLM, despite the weaker direct performance on biomedical NER, are more effective in generating auxiliary annotation data. We attribute this to their decoder-based architecture and extensive pre-train on device open domain corpora, which likely enhance their generating fluency and contextual coverage. So this is enable LLM to produce higher quality and more various annotation. So for the second research question, given augmented data from different models, what is the best strategy to combine them with original label data during training? So to explore this, we evaluate multiple two-stage training strategies that integrate auxiliary annotation generated by LLM into BERT model. So all strategies that demonstrate the performance improve over the baseline. But among the strategy, joint training on NCBI training and LLM labeled validation data in stage 1 achieve the highest F1. So follow closely by two-stage fine-tune strategy and begin with LLM labeled data and then fine-tune on train set. The result suggests that exposing the model to both data sources early, either jointly or sequentially, can be beneficial as long as the human labeled data is emphasized in the later stage. And in this section, we investigate the third research question: what factor of the augmentation set influence the performance of BERT-based NER model? Specifically, we examine whether increasing the amount of auxiliary annotation improves the performance and how this effect interacts with domain relevance. So we consider 3 auxiliary sources and the NCBI. For the NCBI dataset, we have the validation set, we have the BC5 and the BioRed. While all 3 are in domain and BioRed is substantially larger, so it can show in this table. So augmenting NCBI trained with BC5 improve F1 to 89.86, and using larger BioRed set yields further gain F1 that is 19.49. So to assess the impact of data source or domain, we compare the augmenting the proprietary training set with LLM label data from 2 sources, the in-domain proprietary validation set and after domain BioRed corpus. So it as shown in table, in-domain data have a higher performance. F1 is 86.5, then after domain 85.72 suggests that domain relevance is critical when annotation volume had a constant. Thank you for listening.